In this lecture, we'll define second fundamental form on a regular surface. And after that, we'll define normal curvature of a regular curve in a regular surface. Okay, let us begin. Okay. Before going to the second fundamental form, so let me recall the definition of Gauss map. Let S be a regular surface in R3 and n bar from S to R3 be a differentiable unit normal vector field. So this n bar, it gives a orientation of the surface S. Okay. So how I have defined this Gauss map? So suppose this is my surface, and if I take a point P, and if I take the tangent space at the point P, which is TPS, so this n bar P, it is normal vector to the surface, and this n bar P, it is a unit normal vector field. So now this n bar P, so this you can translate to origin. Suppose these are my coordinate axis. So now translate this n bar P to the origin. So this vector n bar P, it is same as the vector n bar P, but here this n bar P, it starts from P, and now we have translated to origin. So therefore, so I have a map from this P to this unit vector n bar P starting at the origin. So therefore, I have a map from this surface S to S2. This is my unit sphere S2. Okay, and now observe that if I take the tangent plane at this point NP, so this is tangent plane at the point NP of the surface S2 unit sphere. So this TPS, this is the tangent plane. So this is parallel to TNPS2. Okay, so this n bar gives a map n from the surface S to S2. And now if I take the differential of this map at the point P, so this will be a linear map from TPS to TNP S2. So TNP S2 is identified with TPS. Okay, so this N map, it is called the Gauss map. So this NP here, it is equal to this NP. And DNP, it is a linear map from this TPS to TPS. So this we have shown that this is a self-adjoint operator. Okay. So now let us consider this quadratic form. Q on the tangent space of S given by QW is equal to the inner product of dNPW with W. So this W, it belongs to the tangent space of S. So let us take, so let U sigma be a surface patch such that this P belongs to sigma U. Sigma U is contained in S. So if I take sigma U at the point P and sigma B at the point P, so this forms a basis for the tangent space of S at the point P. Okay. So now let W equal to, so W, it is a vector in tangent space. So W will be equal to C1 sigma U plus C2 sigma B. So apply dNP on W. So this will be equal to C1 dNP of sigma U plus C2 dNP of sigma B. So which is again equal to C1 the partial derivative of this n compose sigma with respect to U. So this partial derivative del U of n compose sigma is computed at sigma inverse P plus C2 del V of n compose sigma evaluated at the point sigma inverse P. And we have denoted Nu or del N del U, which is same thing as del N del U, to be equal to del del U of N compose sigma. And NV, so this is del del V of N compose sigma. Okay. So therefore, this key QW, so which is equal to the inner product of dNPW with W. So this will be equal to C1 square and inner product of NU with sigma U plus twice of C1 C2 inner product of NU with sigma B plus C2 square inner product of NB with sigma B. So here note that, so I am using this fact inner product of sigma U NB is equal to inner product of NU comma sigma U. So this thing I have proved in the last class. Okay. Now also observe this thing. The N is normal to the surface. So inner product of N with sigma U is equal to 0. Now take partial derivative with respect to U. Okay, so what we'll get? So in inner product of in U with sigma U plus inner product of N with sigma U. So this is equal to 0. Okay, so this sigma U exists. So here I have to assume this S to be a regular smooth surface. Okay, so this implies that inner product of Nu sigma U is equal to minus N comma sigma UU. So similarly, so inner product of Nu sigma B, so this is equal to minus N sigma UB, and inner product of NB sigma B, this will be equal to minus N sigma BB. Okay, so now let me define the second fundamental form. The quadratic form, pi p defined on the tangent space of S is given by pi p of W is equal to minus dnp W, comma W. So where this W, it belongs to the tangent space of S. So pi p of W is equal to minus of QW, and QW is equal to the inner product of dnpW with W. Okay. Okay, so let me just change the language. So the quadratic form pi p defined on the tangent space by pi pw is equal to minus inner product of dnpw with W is called the second fundamental form at the point P belonging to S. Here this minus sign, it is taken in order to define normal curvature of a curve inside a surface. We'll see that thing in a moment. So now let us see, so what will be the local expression of this second fundamental form. Okay, so already we have observed this thing. So if I take this curve, let alpha t equal to sigma ut comma ft. So q alpha prime 0, so this is equal to u prime 0 inner product of nu with sigma u plus twice u prime 0 times b prime 0 inner product of nu with sigma b plus b prime 0 square. So here also there should be square, u prime 0 square. So this b prime 0 square, it is multiplied by inner product of nb with sigma b. So this pi of this alpha prime 0 at the point P. So alpha 0 is equal to P. So QP alpha prime 0 is this. So pi P alpha prime 0 is equal to minus of QP alpha prime 0 so what you will get, so this is equal to u prime 0 square minus of inner product of nu with sigma u plus twice u prime 0 b prime 0 times minus of the inner product of nu with sigma b plus b prime 0 square minus inner product of nb with sigma b. And now let us take, so let L equal to minus nu comma sigma u, M equal to minus nu inner product of nu comma sigma b, and capital N. So this is equal to minus inner product of nb with sigma b. Okay, so this pi p, so with respect to the this coordinate map sigma, it is same thing as L du square plus twice m du dv plus n dv square. Okay, so this L, M, N are called the coefficients of the second fundamental form. So in some book, so this coefficients L, M, N are also denoted by small e, f, g. Okay. Now let us work with an example. Let us take a hyperbolic parabola. So what is the equation of hyperbolic parabola? Z equals to x square minus y square. The surface will be like this. So this point is origin. So let us take this P to be my origin. So we can give a parameterization of this hyperbolic parabola. So let sigma ub to be equal to u comma b comma b square minus u square. So here this paraboloid, it is z equals to y square minus x square. So you can compute sigma u. So it is the basis of the tangent space. So sigma u is 1 comma 0 comma minus 2u, and sigma b, so it is equal to 0 comma 1 comma twice of b. So the normal vector or Gauss map, so n of sigma ub, so this is equal to, so you can compute from here, it is the vector product of sigma u with sigma b and divided by norm of this. So this will be equal to u by root over u square plus b square plus 1 by 4, comma, minus b divided by root over u square plus b square plus 1 by 4, comma, 1 by 2 multiplied by root over u square plus b square plus 1 by 4. Okay. So now let us take a curve alpha t which pass through origin. So alpha 0 is equal to the origin. So let alpha t is equal to sigma ut comma bt. So where alpha 0 is equal to the point P. Okay. So now, so what will be the tangent vector alpha prime 0? So alpha prime 0, so this is equal to sigma u evaluated at the point origin times u prime 0 plus sigma b at origin times b prime 0. So sigma u at origin, so this is 1 comma 0 comma 0 times u prime 0 plus 0 comma 1 comma 0 times b prime 0. So which is equal to u prime 0 comma b prime 0 comma 0. So the tangent vector alpha prime 0 is given by this u prime 0 comma b prime 0 comma 0. Okay. Now we want to compute this DNP at the point alpha prime 0. Okay, so how do you do this thing? DNP alpha prime 0. So this is equal to limit t tends to 0 n alpha t minus n alpha 0 whole divided by t. So it is again limit t tends to 0. So n alpha t is ut divided by ut square plus vt square plus 1 by 4, comma, minus vt whole divided by root over ut square plus vt square plus 1 by 4, comma, 1 by 2 root over ut square plus vt square plus 1 by 4 minus n of alpha 0. So alpha 0 is my origin. So this will be equal to here. So the first coordinate, it will be equal to 0 because u is equal to 0 here, u0 is equal to 0 here, v0 is equal to 0, and here it will be equal to 1. So whole this thing is divided by t, and then I am taking limit t tends to 0. So again, so this limit, it will be equal to, so what you can do here, so in the first coordinate, you can take ut minus u0 because u0 is equal to 0. And in the also second coordinate, you can take vt minus v0. Okay, so now in the first coordinate, you have limit t tends to 0, ut minus u0 divided by t. So which is equal to u prime 0. And u and v, so these are my continuous functions. So ut goes to u0 as t tends to 0, and u0 is 0. Okay, so if I take t tends to 0, so this ut will converge to 0. Okay, so therefore, so this limit, so it will be equal to twice u prime 0, comma minus twice v prime 0, comma 0. Okay, so we have computed the differential of this alpha prime 0. So dnp of u prime 0, comma v prime 0, comma 0. So this is equal to twice u prime 0, comma minus 2 v prime 0, comma 0. Okay. So now from here, so it can be easily seen that, so this 1, 0, 0 and 0, comma 1, 0 are eigenvectors of this linear operator DNP with eigenvalues 2 and minus 2 respectively. Okay. And so what will be the second fundamental form? The second fundamental form pi p of alpha prime 0. So this will be equal to minus of inner product of dnp alpha prime 0, comma alpha prime 0. So this is equal to minus of twice u prime 0 square minus twice of v prime 0 square. Okay, so therefore this will be equal to twice v prime 0 square minus twice u prime 0 square. Okay, so yeah, so this will be of this form. So L du square, so minus 2 du square plus 0 du db plus twice dv square. So therefore L is equal to minus 2, m is equal to 0, and n is equal to 2 here. Okay, so now let me define, so what do you mean by normal curvature? So let us take C be a regular curve in S. Okay, so passing through a point P, and let K be the curvature of C at the point P. Let small n be the unit normal vector to S at the point P. So let us take this k to be k of P and n to be n of P. So n of P be the unit normal vector to S at the point P. Okay, and let us take, so let cos theta to be equal to the inner product of this NP with capital NP. So capital N, it is the Gauss map. So let us take this theta to be theta P. So theta P is defined in this way. So cos theta P is the inner product of NP with capital NP. Okay, so theta is the angle between the normal vector and the normal to the surface. So NP is the normal vector to the surface. The number Kn P equal to Kp cos theta P is called the normal curvature of C, which is contained in S at the point P. Okay. Let me draw a picture. Suppose this is my surface S, and let us take a point P. And we have a curve C passing through this point P. Now, we have two vectors at this point P. So one is normal to the surface, that is capital NP, and one is normal to this curve, small np, which is also orthogonal to the tangent vector to the curve at the point P. So let me draw this tangent vector to the curve. Let us call it to be C prime 0. And now I have these two vectors. This is my capital N, which is normal to the surface. And I have another vector which is small np, which is orthogonal to this tangent vector C prime 0. And this theta, it is the angle between this capital NP and small np. Okay, And then what we are doing, so we are taking the projection of this capital NP on the line passing through this cap. Okay, let me repeat. So we have this small np. So what we are doing here is the following. So this Kn, let me write down. So Kn is the length of the projection of the vector Kn over the normal NP to the surface at P. Yeah. So we are taking this Kn and then we are taking the orthogonal projection on this NP. Yeah, so let me explain again. So we have this small NP, which is normal to the curve. And if I take this line, so somewhere here, so I'll get this Kp multiplied with this normal vector NP. So this point I'll get. And then you take the orthogonal projection on the line passing through capital NP. So this length is K suffix N. Okay, so K suffix NP is this length. Okay, so now let C be parameterized by alpha S. S is the arc length parameter of C, and alpha 0 is equal to P. So now this N of alpha S, capital N of alpha S, comma alpha prime S, if I take the inner product of this N alpha S with alpha prime S, so this will be equal to 0. So now if I differentiate with respect to S, so what I will get is the following. Inner product of N alpha S with alpha double prime S. So this will be equal to minus N compose alpha prime S, comma alpha prime S. So I'll get this thing. And now, if I take pi p of alpha prime 0, so this is the second fundamental form. So this will be equal to minus of inner product of D and P alpha prime 0 with alpha prime 0. So this will be equal to minus of n compose alpha prime 0, inner product of n compose alpha prime 0 with alpha prime 0. So this will be equal to the inner product of n of alpha 0 comma alpha double prime 0. So now recall that, so alpha double prime 0 is equal to Kp times Np. So where Kp, it is the curvature of the curve alpha, and Np, it is the unit normal vector of alpha at the point alpha 0, which is equal to P. So this will be equal to inner product of n at the point alpha 0, which is equal to P. Alpha 0 is equal to P. So therefore, inner product of Np with Kp times the normal vector small np. So this is equal to K suffix np. So this is the normal curvature Kn I am getting. So therefore, this second fundamental form, it gives you the normal curvature. The second fundamental form pi p of a unit vector V belongs to PPS is equal to the normal curvature of a regular curve passing through the point P. And tangent vector of this regular curve at the point P is B. So let me end with a proposition which will be not proved in this course. All curves lying on a regular surface and having at a given point P belongs to S, the same tangent line have at this point the same normal curvature. Yeah, so this proposition, it says the following. Suppose you take a regular surface S inside R3, and if I take a point P and take a tangent vector, let us take, and now you can have different curves whose tangent vector is this given vector, say B. So then the normal curvature of this alpha and beta at the point P are same. So the normal curvatures of yeah, so the normal curvatures of alpha and beta at P are same. Okay, so we'll stop here.